Yesterday, we talked about proving type safety for the simply typed lambda calculus using a unary logical relation, right? So I thought I'd put up on the board where we left off yesterday. And today, what I'd like to do is basically extend our language with recursive types and see how we extend this logical relation approach when we have recursive types in the language, okay? I've already alluded to various circularities that arise when you have recursive types, so that's the point of today's lecture. And in particular, we'll talk about how to extend this logical relation that's up here to what we call a step-indexed logical relation. So this is an introduction to that technique. Okay, so you guys have seen recursive types in your earlier lectures, right? So you've seen typing rules for fold and unfold? Yes? All right, good. Let's start with that. Okay, so the types in our current language, yesterday we had booleans and functions, and now we want to add recursive types. So I have alpha, a type variable, and my recursive type's mu alpha tau, right? For our expression language, we have exactly what we had before yesterday. Lambdas, application, variables, true, false, if then else. But let's add the new syntactic constructs that we need for this language. So what do we need to add? Fold and unfold, right? So we'll add an expression fold E, which is the introduction form for recursive types, and unfold E, okay? Which is the elimination form. So as I said yesterday, you first put down your language and then you start to think about how to define the logical relation. So that's why this is our step one, right? Let's get down our language. So let's write down the operational semantics and the typing rules that we need for this extension. And then we'll go and start thinking about how to modify our logical relation, right? Okay, so again, we're doing call by value, simply type lambda calculus, but this time with recursive types. So let's specify the value forms. So it's what we had yesterday. We had true and false and lambdas, of course. And now what's the value form that we need for recursive types? What is the value that has the type mu alpha tau? Fold V. Okay. That is the canonical value form for recursive types. Okay? That's the thing that has type mu alpha tau that you can't evaluate any further. All right, and just to put down evaluation context for the language, again, we had whole, we had stuff we had yesterday. And, well, let me put it down. So for application, what did we have? We had ifs, you evaluate the test, etc. And then this is call by value. So for application, we want these two forms in our grammar, right, which say first evaluate here, then evaluate here. So now what do we want for the new additions to our language? We've added fold E and unfold E. Unfold. So basically, you're saying that when we're here, we better evaluate this expression down to a value before continuing, right? But what about when we're here? Tell me why. That's right, because I already said the value form we want is fold V. So how are we going to get to this value form if we have in our hands a fold E, right? So we need to take this E and evaluate it down to a value. So I'm going to add this context, which says evaluate under the fold till you get to a value, and then unfold E, which says if you have an expression here, evaluate that down to a value before you continue, right? Yes? This V big E right here? Okay, did you guys talk about evaluation contexts last week or something? A little bit? Okay, so the way that evaluation contexts work is they're specifying an order of evaluation. And the way you should read this is that when you have something in the whole, you need to run this down to a value, right? So what this one says is if you have an application form like this, so this is V space E, V applied to E, right? If you have an application form like this where you have a value sitting in this position, then ignore that position, go over here and start running if you have an expression here, start running that down to a value before you proceed, right? Whereas before we even get to that, we're looking at something like this. We might have an E1 applied to an E, right? So if you have an expression in the function position, evaluate that down to a value. Basically, I'm specifying a left to right evaluation order here. Yes? So are we going to understand this as basically a shorthand for a bunch of congruence rules? it's a succinct way of writing down operational semantics. And I'm sorry, I thought it was covered last week. So. What? Sorry? Oh, the dot bracket, that means whole. That is your most basic evaluation context that you can have. Okay? So that is a context. Think of it as, yeah, it's basically, it's just a hole. So you can plug this hole with any expression e, little e this time. And it means whatever's in the hole, you run it down to a value. And then you do whatever is around the hole, so to speak. But notice that if my evaluation context is nothing but this, then when I plug it with an expression, which we write as that, this is just e, so that means just run it down. Okay, on the other hand, if I have a hole, let's take something like this. If I have a hole, or something like this, if I have a hole that is going to get applied to true, let's say. It's not a good example. Maybe it should be something else. Or it could be some more complex expression here, right? If this is my evaluation context E, then when I plug this evaluation context with an expression E, which we write like this, then what do we have to do? Well, basically we have to, this is equivalent to E in the hole applied to the value true. Okay? And what it says is run this thing down to a value. When you have a value, then focus your attention on the thing that we're applying it to. Make sense? Yes?
Is there a side condition? Because in the application case, there's some possibility of ambiguity between whether you provide big E, little e, or VE. Is there some side condition that says that the whole cannot?
No, the side condition is specified right here by how I have picked my grammar, right? So this one says, look at this position first. Even if you have an expression sitting over here. You might have an expression sitting here or a value sitting here, and I don't care, right? Because values are little v's are little e's, right? Values are expressions. So you could have a value sitting here or an expression, I don't care. You have to focus your attention on the leftmost position first in the application and get that down to a value. Once you have done that, once you have something that looks like a VE, then focus your attention on this position. That's what this rule is saying. That if you have an application where you have a value form followed by some...
What prevents you from applying the big E to the small e? Why does the big E, little e rule not apply to little e, little e?
Oh, this is saying that somewhere deeply nested in here, there's a hole.
And so, right, so why couldn't that hole be the V there?
There's no V in the E grammar.
Is that what
You're saying, so a V is not a potential E. I mean,
is that what you're saying?
yes.
Okay.
Look at the grammar, right? What is the base case? It's a hole. So the simplest possible thing you can have that is a big E is a hole. It can never be a value, a V itself. You can plug one of those with a V. That's completely okay. But a value or an expression is not an evaluation context, because an evaluation context is something that has a hole in it somewhere that you're going to plug with some sort of expression. Okay? If it helps, I could write these rules in a different way, right? The way they're written in TAPL, which means just spelling them out and writing a whole lot of rules for every single one of these cases in order to specify a call by value left to right evaluation order. And I assume you're all comfortable with doing that, right? So I'm going to move on. Okay. Okay, so everyone does know how to write, specify operational rules, right? In that style? Good. Okay. All right. So we're not done with our operational semantics yet. We need to specify our step relation, our small step relation, just like we had yesterday. So basically, anytime you have an E steps to E prime, then an evaluation context with that E in it steps to the same evaluation context with the E prime in the whole. And then, of course, we have our reduction rules, which are our primitive reduction rules, which, of course, are the ones from yesterday. I'll just write down the application rule, right, the beta rule, E with V for X. And let's write down the interesting part, the new rule for today. So how do we evaluate? What's our primitive reduction rule, based on what's on the board, for recursive types? So I'm asking you to imagine that if you had a fold e, little e, somewhere in your program, you've evaluated that down to a value. So it might be a fold v now, right? That's a value form. What can you do to these value forms? You can unfold them, right? So you want to be able to do something like this. How does that run? If you encounter an expression like that, what will you step to? Yes? A bunch of people said it. V. Okay. Right? An unfold is essentially getting rid of that fold tag that's sitting around the value. Right? Okay. So, the typing rules for this. So we have our type system for simply type lambda calculus. I won't write those rules again, but let's talk about the rule for fold. So I have expressions of this form in my language now, right? Gamma, just like yesterday, maps variables x to types tau. So what's the typing rule for this? Sorry, how do I type check this? Fold E, I already said fold V is the canonical form for recursive types. So this is going to have type mu alpha tau, right? And that has type mu alpha tau if E has type tau with mu alpha tau for alpha, right? I mean, I hope you guys talked about this last week, that this is how recursive types work. That fold and unfold are essentially your witnesses to a view shift, right? Unfold takes that type and gives you the expanded out type, right? And I think you did examples with lists, for example. Maybe even trees, I'm not sure. So unfold expands your view of the type, so to speak, by substituting mu alpha tau for alpha, right? And fold goes the other way. Right, that's all they are. They're just like syntactic little syntactic markers in the language, in this calculus, which witness this view shift. And they allowed us to write these typing rules which sort of capture that view shift. Okay, so the unfold rule is just going to go the other way. So if E has type mu alpha tau, then unfold of E has type tau with mu alpha tau for alpha. Right? Okay, so our language is up on the board. Now let's think about what we want to do to prove type safety for this language. So in particular, you know that this language is now Turing complete. It has non-termination. Our language yesterday did not, right? Programs can run forever. Okay. And it's a little worse than that, but we'll get to that in a second. So you also saw last week that you can use recursive types of this form to type check, for instance, omega. Right, lambda xx applied to lambda xx. How do you actually write that as a well-typed term? You guys did this? Yes? Okay, good. Thank you. All right, so let's move to our logical relation. So our goal is the same as yesterday, right? I have a definition of what I want out of type safety, right? What it means for an expression to be safe. And we're interested in proving the type safety theorem, which says that if you have a closed term E of type tau, now it just has recursive types in the language, we want to prove that E is safe. Okay? And we're going to do this exactly like yesterday in two parts by proving this lemma A and lemma B. A is going to say that if E is well typed, then it's in the logical relation. You can think of this as semantically well typed, syntactically well typed and semantically well typed. Okay? It's in the logical relation. And if you have a closed term E in the logical relation, then it must be safe, right? And we saw yesterday that proving B was really easy, and proving A is where all the hard work is, right? And those two put together, if you have A and B, you get your type safety theorem, right? Okay, good. So here's our logical relation. It's defined by induction on the structure of the types. We saw this yesterday, right? So today we need to extend it with an interpretation for recursive types. I very strategically left space there, right? Okay, so just to review this idea of it's defined by induction on the structure of the types, right? We didn't go over this super carefully yesterday, but let's do it now. So when we give the value relation for Booleans, notice that we we're not using any value interpretation or V relation or E relation in the definition. So this is good. When we define the case for tau arrow tau prime, notice that in the definition, we only refer to V of tau, which is a smaller type than tau arrow tau prime. And here, we only use tau prime, which is also a smaller type, right? So we are making sure that this is inductively well defined. We are never using a bigger type. Where else? Of course, there's the V and E shift, but that's okay. E is still working. Here, we're appealing to the E relation, but at a smaller type tau prime, right? And now if we go look at the E relation, well, the E relation for tau doesn't really get smaller per se, because it appeals to the V relation for the same tau. But this is okay, because when the V relation calls E back, it actually makes the type properly smaller, right? Strictly smaller. Okay? So this is why this is a well-founded relation. All right, now let's handle the case. You are smiling because you know what's coming, right? Okay, so let's handle the case for recursive types. So again, same question from yesterday. I asked, what are the value forms that belong to the value relation at this type? What values have the type mu alpha tau? Okay, fold V. The only shape of value that can have this type. Okay, so now we said when we define these relations, we have to think about, essentially we're building this relation so that any terms we put inside it have the property of interest, right? I kept saying that yesterday. And the other thing we have to do is that for every single one of these types, we want to make sure that whatever needs to happen for the elim form to preserve that property, that we're somehow specifying that in the relation. So in particular, for lambdas, we said that the elimination form preserves the property of interest, right? And we did that by saying, if you give me inputs that have the property of interest, I will give you outputs with the property of interest. So now we have to do that same thing for recursive types, right? So let's look at recursive types. If I have a fold V here, this thing has type mu alpha tau. If you look at the typing rule, that means that the V has what type? The substituted type, tau with mu alpha tau for alpha, right? So we need to say something about what? Well, I'll sort of try and attempt. If we apply our elimination form, unfold, to this fold V value that we have, we'd like for that thing to have the property of interest, right? In the E relation, at what type? Unfold, fold, steps to, up there, unfold, fold, steps to the V, right? So it would have to be the same type as the underlying V, which is tau with mu alpha tau for alpha. Correct? And then right at the end of class yesterday, I said, oh, sometimes, you know, we don't write out the full elimination form. I know that an unfold of a fold is in one step going to reduce to a V. So why don't I just make this a little more succinct, okay? Equivalent, but more succinct. I'll just write it as V is in. And now I can say V relation because it's a value. Two ins. Okay. Yeah, problem, right? Not so good. Not inductively defined, well, not inductively defined anymore. So this type mu alpha tau, right, when we define the interpretation for that, we better not be doing it by appealing to the definition for any bigger types. But we are. This is a bigger type. Tau with mu alpha tau for alpha is a bigger type than mu alpha tau. So this is no longer a well-founded relation. This is a circularity, the kind of circularity that arises because of recursive types. So we have to do something to make this relation well-defined again. All right? Okay, so this is where the idea of the step index logical relation comes in. We're going to appeal to a new intuition when defining these logical relations, all right? Which is the following. Instead of just defining these relations, which are, by induction on types, on the type structure, we are going to define relations, not just by induction on the type tau, but also index them with a natural number. So k is a step index here. It can be 0 or more. Okay? All right. And what's the intuition for this? And we're going to say that these are inhabited by values under some conditions. That's going to be the shape of the relations that we want now. And let me say what that means. So the intuition here is, before I was reading it as whatever value I have here, this V looks like it has this type tau. Right? Now, there's an added level okay, so the way we want to read this now is say this V looks like it has this type tau for up to k steps. So if you run for more than k steps, it may not actually behave like a value of type tau. Okay, but V looks like it behaves or will behave like a value of type tau for up to k steps. That's the intuition. Okay? Another way of saying it is that your assumption that V has type tau is not going to be violated for up to k steps. After that, all bets are off. Okay? All right. So why do we want to do that? Well, let's sort of go through and look at what would happen if we started, indexing our relation with these steps. So again, let's just focus on one part of the definition at a time. So if I want to say that true and false look like they have type bool for k steps, do I need to sort of add any conditions to check for that? No, right? Because they have the type bool for any number of steps. So we're good. We didn't have to do anything. I just added an index, and I don't have to augment my definition. All right. Now let's think about lambdas. Now I'm asking, when does lambda x dot e look like it has type tau or tau prime for k steps? I'm giving you a lambda, you have k steps. You can't run for longer than that, so to speak. Okay? All right. Well, before we said that you have to give me a value and I plug it in, etc., right? Okay, now I want you to think about this in terms of a timeline. We are right here in the timeline. We have k steps. Okay? And this is where we have in our hands, we have this lambda. And we're trying to figure out if it actually looks like something of type tau or tau prime for k steps. Okay? Now, the question is always, what can you do with this lambda, right? Because I'm saying it has to behave like a tau or tau prime for k steps. The question is, okay, you have k steps. What are you going to do with it? What are you going to do with the lambda? Apply it. Are you going to apply it right now at k steps? Not necessarily, right? It's a value. You might be at some point in your program where you have something like, maybe you're doing one of these. You have your lambda right here, and then it's being applied to some e prime, but you can't really apply that lambda yet to a value, right? You have to go run this e prime down to a value. Maybe you have to do other computation in other parts of the program, so to speak, until you can get to the position where you can actually do an application, right? And call by value, you have to have a value sitting there. Only then do you do the application. So we have k steps. We might run for a while, but at some point in the future when we have j steps left, where j is less than k, at that point, imagine that you are going to actually do this application. At that point, someone is going to say, oh yeah, you have your lambda? Apply it to this value v. Okay? So at some point in the future when you have j fewer than k, fewer than or equal, because you could do the application right now at k steps as well, but imagine that you can also do it in the future, right? Okay, this should be at less than or equal. All right, so at some point in the future, someone's going to give you a value, and now you're actually going to do the application, all right? But application eats up one step, right? In beta reduction is going to eat up a step, and this lambda applied to v is going to step to e with v for x, right? Okay, so let me edit this a little bit. Imagine that at some point in the future when you have j plus 1, someone comes along and is ready to give you a value, but then you take one more step, and that's when you actually plug in the value. You have to take that one step. And imagine that here, or rather, right here, when after the beta reduction, you have j steps left. Okay? So, at some point in the future, you have this thing. So what I'd like to be able to say here is that lambda looks like it belongs to tau or tau prime for k steps if for all j less than or equal to k, at some point in the future, you give me a value that is good a value v, for all v, that looks like it has the argument type tau for j steps. Okay? Some point in the future, you give me a value that will behave like a tau for j steps. And if you do that, then after my beta reduction, my computation will behave like it has the type tau prime for the remaining j steps. Make sense? Okay? All right. So that's what we do with lambdas. Any questions? Yes? Good. Good question. This is a tiny little subtlety, and that's why I was trying to sort of bring it out. The thing is, you could make a j plus 1, but you don't need to. Because I was trying to emphasize that you will eat up one more step before you can actually touch that value v. So imagine that your function was just lambda xx. You still, at j plus 1 steps, why should I demand that you give me a value that's good for j plus 1? Because I'm going to eat up one more step, and it's not really until I have j steps left that I can start sort of poking at that value and seeing if it behaves right, so to speak. Okay? So that's why we are saying that from this point onwards, the point after the beta reduction, your value better be well behaved. So this is a slight, but it also gives you an idea of like how I'm appealing to this operational intuition of how many steps a program takes to sort of justify this semantics, right? This specification. Yes?
Why didn't you hear the argument is, why is it not enough that when you do substitution?
This came up yesterday, right? We said, I sort of talked about this slogan of logical relations, that if you give me inputs that have the property of interest, only then can I promise you outputs with the property of interest. And this thing right here, where we say, you give me an argument for my lambda that has the property of interest. That's how we read that, right? It better behave like a value of type tau. In this case, we're just adding step indices there, right? But we had that condition there yesterday as well. Yeah?
Since we're going to eat up one step with our function application,
Yeah?
don't we only need for all j less than k, not less than or equal to?
I don't think it matters either way. So this is really governing, you just want to make sure that you never appeal to, this is fine because, I see what you're saying. It would work, yes. Some of this is, you go for the best. Yeah?
Yeah, sorry. So I see that the argument needs to be well behaved.
Yes.
Why is it that you have we not use any index at that point?
Right here? No, you can't use any index because now what I'm trying to do, before my logical relation was well-founded because it was defined by induction on the structure of types. Now what I'm trying to do is I'm first trying to make it well-founded by, I'm defining it by induction on this natural number and then by induction on the structure of types. Okay? So I definitely do not want these numbers ever to go up by 1. Okay, because the outer induction is on that natural number. And let's look at the case for recursive types because this will make it clearer. Okay? So how do we, the only reason I introduced this is so that we could deal with recursive types, right? So let's ask ourselves the question, when does a value fold V look like it has type mu alpha tau for k steps? Again, what do you do to a fold V? You unfold it, right? Unfolding it takes a step, eats up a step. That's what saves us. So this underlying value V, we only need it to be in this bigger type at k minus 1. Right? That's all we need. Because the only way we can get our hands on this V that's sitting inside the fold is if we apply unfold to this fold. And that is going to eat one step up and leave us with this value. That means we have now only k minus 1 steps left. And that means that our requirement should, for this belongs to this type for k steps, only needs that underlying value V to behave like a value of this bigger type for one fewer step. See, so what have I done? My type got bigger, but I don't care anymore because my outer induction is now on this number. Right? So this relation is now well-founded. It's inductively well-defined because it's defined first by induction on this step index and then by induction on the type structure. Yes?
Can you explain again why with the
You can do it. If you want to do it, you can totally do it. It'll work either way. It'll work either way. The proofs will work either way. It doesn't matter. Yeah. Yes? Wait. He just asked the same thing, right? Here? Here? It can be strictly less, or it can be less than or equal. Both will work in the proofs. Okay, so maybe now is a good point to say this next part. When you are first introduced to step index logical relations, you will find that sort of seeing what's going on, it's really, really helpful to think about the steps that are being taken, okay? And I mean, it's essential to some extent. But as you gain more experience with them, you'll start to see that once in a while, it doesn't really matter if you decrement the step, even though you know that right there, you're going to have to take a step in the operational semantics. It's a step budget. Sometimes you can be a little bit more flexible with it. And this is a perfect instance of that. I can give you another instance of that, which actually shows it even better. We talked about pairs yesterday. Let's put it here. V of tau 1 cross tau 2, right? I said, imagine that you have pairs in your language. How will you define this relation? And we said, well, a pair of a V1, V2 looks like it has type tau 1 or tau 2 if V1 looks like it has type tau 1 and V2 looks like it has type tau 2, right? Let's edit this definition so that we now are able to have pairs in our step index relation. So, when does a pair look like it has type tau 1 cross tau 2 for k steps? This is an answer to your question and your question. When V1 has type tau 1 for how many steps? K. See, so now the purists right now will say, but you can't get your hands on that V1 that's sitting in the pair without doing a first, and the first of the pair is going to eat up a step. So you have to put a k minus 1 here, right? If you're really being strict about your operational steps and counting them super carefully, you would put a k minus 1 in both of these positions because you can't get to those values without applying a first or a second. But, you know, we're using these step indices to make this logical relation well-founded. And in this case, since your type is already getting smaller, you don't need to reduce the step index. So just do the easy thing and leave it at k. Okay? So this is what I mean. You have to be a little bit... The operational intuition helps, but you don't have to adhere to it too strictly. Okay? You just need to adhere to it. Like if you have a definition where your type is getting bigger, like right here, then you really need to go and pay attention to your operational semantics and figure out if it takes a step so that you can actually decrement the step index. That's the key. There was a hand up here. Yeah.
It's like, if I'm thinking in terms of formalizing this in Coq,
Yeah.
then I will want to reduce k right away, just because that'll make it easier in Coq, right? Like that's the easier thing to do.
I don't think it's...
Rather than like being sure that the sum of the k index plus the type here.
All of this relates to what exactly happens later on in the proofs,
Sure.
right? Because, yeah. And there you can sort of...
I mean, just for Coq to accept it as well.
Oh, just for Coq to accept it. But Coq should... Here, you have to explain to Coq that the step index is going on. Yes, but in other places, you are doing induction on the types. So the type is getting smaller, so Coq should accept it, even if the step index doesn't go down. Right? Again, it's two levels. So what I'm saying is, if your type is becoming smaller, then you don't need to push the step index down. It's only when your type is actually becoming bigger that you need to make sure the step index goes down, so that you get an inductively defined definition. Yes? Good question. What is a V0? When does a value look like it has this type for 0 steps? This is actually a much more interesting question for the E relation. Let's come back to it in a couple of minutes. Let's edit the E relation and then ask the same question. Okay? Because at 0 steps, you have no discerning power. So anything should look like it has any type. Right? Yeah.
Is it fair to say that, like, the work thing that something that takes infinitely many steps should be counted infinitely many times? I mean,
Yes, then that's...
Just decide whether something can take count or not?
You're right. That's what's happening in the fold, right? Or for recursive types. You could keep, you can use recursive types to code up an infinite loop, which means that you're going to have an infinite number of unfolds of folds in that computation, which means that you better, in a sense what you said, right? They better be counted infinitely many times. Right, exactly. Okay, so the E relation. Expression E behaves like it has type tau for k steps. How do we say that? Again, a timeline. You're right here. Oh, by the way, this timeline ends at 0, right? After that, we can't do anything. All these timelines are very strategic with respect to that. Okay, so in the case of the E relation, I want to know if E has type tau or behaves like it has type tau for k steps. Okay, so I have my E over here. So what do I do with it? Well, the definition's already saying go run it. But this time we have a budget. We can't run it for more than k. Okay? So what we're going to say is for all j, I'll make it strictly less than k, for all E, if it steps to E prime in j steps. So right now we have k steps. Suppose that this E is not a value, and it eats up an actual budget of j steps to get down to something that is irreducible, which is my E prime in that figure. Okay? And now after that, I can't reduce it anymore. I can't take another step. So I've eaten up j steps, so right now I have j minus 1 left. Right? Okay. So what's just happened is I've said, run this down, and if you get to something irreducible in something less than whatever my budget is, then that E prime better look like it's a value of type tau for the remaining number of steps, which is k minus j. Yeah? Questions? Sorry, why is it? Why is it strictly less than? Well, the intuition here is that if it goes back to that 0 question. After 0, we really can't tell anymore. So why do I even care about something belonging to something for 0? Okay, that's why. Okay, so I draw these timelines because, in one definition we're doing a k minus j, and the other one we're just using a j, but I think staring at the timeline makes it really clear why, right? In this definition, we have an E that's good for k. All we can do is run it till it becomes an irreducible thing. We eat up a j step, so we have k minus j left. That's why we have to say that the resulting term E prime has to be in the value relation for the remaining number of steps, k minus j. Okay, we do a similar exercise, and we start putting k's on everything, really. So substitutions belong to the interpretation of the gamma if this belongs to g of gamma for k, and the value looks like it has type tau for k steps. Nothing more. What do we do at the top level? So notice I'm going to have to put a step here and a step here. Let's think about what this last definition is trying to say. Right? It's trying to say that I have a term E that has type tau, but this term is open, and it contains variables from this environment gamma. Right? Now I really want to make a statement about any number of steps. And why do I want to do this? Well, because ultimately I'm interested in this theorem which says if something is syntactically well typed, then it's semantically well typed. In other words, it's safe, right? So semantically well typed should say that for any number of steps k that you might choose to pick, things are good. Okay, so we're going to say for all k greater than or equal to 0, if you can give me a substitution that's good for that number of steps k, and I use that substitution to close my term, then that closed program is good for k steps. Okay? So at the top level, we make this statement about all k. But notice the only reason we did this is so we could write down a relation that was obviously well-founded. Because when it's obviously well-founded, you know that you haven't defined something silly that is an empty relation. Right? That's basically the goal of like inductively producing this definition, right? Okay. And this gives us confidence that we haven't accidentally produced an empty relation. Okay. All right. Yeah. Any questions? Yes.
So when you're in the definition of safe, you say for all k equal to 0. But my intuition is it takes something like this to get to actually the definition of behavior and
In this safe thing right here? Yes, that's a great point. Let's talk about that. That's exactly what I want to talk about next. So your point is really about, your concern is really about lemma B. Okay? Because lemma B, and I'm leaving the statement exactly as it was before, it's just that buried inside this definition, we have a for all k greater than or equal 0 statement now, right? So let's quickly go through how we are going to prove this lemma B, right? Because he's saying, well, here you have a star. You're taking any number of steps. Like, how does this fit together? Now, before I continue, let me sort of clear up one thing. Yesterday, I just put a star there, right? And star was not necessarily transitive closure. It was like you take some number of steps and you get to E prime. Notice I didn't say that this E prime is irreducible. I was just saying you have an E, you take some number of steps, you get to an E prime. Either this E prime is a value or it can take another step, right? So really, this star is a stand-in for some n, right? Okay? All right. So, having made that observation, we want to prove lemma B. So we want to prove that some E that's in our logical relation is safe. So in order to prove that E is safe, what do we have to do? We have to say, I'm just going to do this verbally if that's okay. Is that all right? Okay. And if you want me to write stuff, please let me know. Okay. So in order to prove that E is safe, we're going to say, okay, suppose that E takes n steps, some number n, and this can be, we can actually be more formal and say n is just some natural number, right? So E takes n steps to get to some E prime, and now we are required to show that that E prime is a value or it takes another step, right? So that's what we still have to show. Now we're going to go use our premise, and our premise says, yeah, for any number of steps that you choose to pick. Okay, so let's pick n. All right, so we instantiate this k with n, and we don't have to worry about substitutions because our term is closed for lemma B. So that goes away. So then we're left with E is in the E relation for n steps, right? Because we picked k to be n. All right. So now from E belonging to the to the E relation for n steps, this definition right here, we still have to show our goal, right? Which is the right-hand side of the safe. All right. So we know that E belongs to the E relation at type tau for n steps. That means that for all j less than k, okay, so we instantiate, there's a strictly less than here. Maybe we should pick an n plus 1 there. I have an off by 1 error. We should instantiate our k with n plus 1. That will give us that E belongs to the E relation for n plus 1. When we get over here, we want to say that we know that our E steps in n steps, but n has to be less than n plus 1, right? Now we're good. Okay? So we say, yes, we know that E steps to E prime in n steps, and we do the same argument as yesterday. Either it's reducible or it's not, right? If it's not irreducible, then of course it can take another step and we're done. If it is irreducible, then this lemma tells us that it belongs to the V relation and therefore it must be a value, right? Good? Concern? Yeah? Right. But that was interesting too, right? That picking n was not the right thing there. Because here I needed a smaller number. And I know that E steps to E prime in n, so I had to have picked a bigger k up there. And this kind of thing happens when you do the proofs. Yes?
Would it actually be a problem, though? Because if you had for all j less than 0, that's just vacuously true because no f number is less than 0?
Well, we're... actually, you're right. It would have worked. Because of the way our value relation is defined, even if these are zeros, we know that whatever belongs to them are values. That's why it would work.
Oh, okay. I was thinking like...
Yeah, you were thinking something else. But that's why it would work. Yeah.
But doesn't mean E, that would not only go as, even if we chose n and n plus 1, wouldn't that only go that E is the E prime is in for one more step?
Yeah. See, again, these are little... It doesn't matter. Why not? As in nothing goes wrong as such, right? So which part do you want to prove? Like what exactly is the
The program takes some more steps. The lambda x doesn't suddenly explode into something terrible.
but we don't care about proving that, right? If you think about the lemma that we're interested in proving, it's this B, right? And I very methodically went through, okay, safe E is the thing that we want to prove. That means that we say, suppose that for an arbitrary n, E takes n steps to get to this irreducible E prime, right? If under those assumptions, you are required to prove that you have a value or you can take a step. Yeah? So it works out. It's fine. Because at that point, all you care about is the n budget that you have. And you don't care what happens afterwards. Yeah? Mm-hmm. It just means that E prime belongs to val if it is in the grammar for values of the language. I was just using it shorthand for that. So it is of the form, if you look at the grammar for values, it's of the form true or false or lambda or a fold V.
So how do we go from V, so when you say
Here.
-1 and j to n, how do you go from V1 of tau to val of V prime?
V1 of tau, where? Here?
Yes, so our argument was that we said j to n and k to n plus 1, right?
Yes.
And then we said that E prime is irreducible, so it belongs to V n plus 1 minus n, which is V1 of tau.
Yes.
So now how do we go from, so E prime in V1 of tau, how do we go to val of E prime?
If E prime is in any number, let's put a 1, of this, if you have this, then you go look at the definition of the V taus. And every value relation has sitting inside it only things which have the value form. Yeah. We built the value relation so that only contains values. So anytime someone tells you that an expression belongs to the value relation, you immediately know that this implies val of E prime because it's grammatically, according to the grammar of the language, it's a value form. Good? Yes? In the definition of safe, it's just saying for any number n, if you happen to take n steps, you need to prove this statement. And that means you can take 1 or 5 or 100. But under the assumption that you are able to take some number of steps to get here. Right, yesterday I had a star there, but really that was the same thing as this more expanded. Yeah, okay. Yeah.
Maybe you already answered it, but what is the difference relations when the index is 0 or negative?
Sorry, say that again? What's in the?
When the k is less than 0,
Yeah.
equal to 0, what is exactly?
These relations are not defined when k is less than 0.
What
K,
when it's 0 exactly?
when it is 0, good question. Let's look at that. So in particular, let's look at when does some expression E belong to the E relation at 0 steps? Right, what does it say? E, imagine that k is 0. E belongs to tau for 0 steps if for any number strictly less than 0, something is true. But these relations, if you really want, I can write that j has to be greater than, these have to be natural numbers, right? There is no natural number that is smaller than 0. And so any expression E whatsoever looks like or behaves like it has type tau if you only have 0 steps left to run. Okay? Yes. And that's sort of the magic of this technique, It's almost, for those of you sort of more familiar or more comfortable with co-induction, it's almost trying to let you say something that's rather co-inductive but in an inductive fashion. Notice what's going on with this. At 0 steps, I know nothing and therefore everything looks good to me, right? At 0 steps. So if I try to define, the set of all terms that look like they have some type tau for k steps, right? When k is 0, this set is, when k is 0, 0 should be somewhere out there. This set is really large. And what we're doing by giving you more and more and more steps is the ability to refine what you know. And when we say for all k greater than or equal to 0, we're allowing you to reason about something behaving like something of type tau for any number of steps. right? Infinity. So with more, as you have more and more steps, you essentially keep refining your set until, at some point, at infinity, you know exactly what behaves like something of type tau. If that makes sense. Lots of hands. Yes?
So, how are you going to define V0 mu alpha for tau?
V0? So see, with the V relation, to be honest, we kind of play this game. We just want to make sure we have well-foundedness with the steps. So I've always found that asking the question, when does something look like it has type tau, for 0 steps, I found this question to be sensible when we're talking about the E relation. You can think of the V relation as sort of a convenience that's just letting me factor my definition in a certain way. So, yeah? I should have said, let's write this differently, actually. For all j, such that j is, we can put a check here if you like, that j is actually a natural number, but it has to be strictly less than k, and now I'll put j here, right? This is slightly more general than what I had before, right? They're equivalent, actually. You can use either one. So now I'm saying fold V looks like it has type mu alpha tau for k steps. If for any j strictly less than k, V looks like it has the expanded type. Okay? I don't like to put those 0 things there. I'm going to light it. It's just kind of a bit messy. Let's go with for all j strictly less than k, and I want you to assume that I always mean that these numbers have to be natural numbers. Another hand? Yes?
The whole discussion when you started with n equals to infinite n equals 10.
Yes.
And then you back with the saying n should be actually n. Why do you need to even go? Because we said that n can be anything. We can directly
N can be anything, and the proof will work out, whether it's n or n plus 1. Yes, I completely agree. Yep. Yes? Yeah?
So if you end up with a value that like few steps, like 1 or 2,
Mm-hmm.
and even then it would be in the relation for a much larger k. Is that fine? Like if it's, if k is equal to 100,
Yeah.
then we say k is equal to 1, then there's a value that is okay for 1 step.
Yes, you know why that is? Or this is more general than the k minus 1 thing, right? So imagine the k is 100. Before my definition said the underlying value should be good for 99 steps, right? Okay, but now I'm saying that it can be good for 1 step or 2 or anything all the way up to 99. Now let's think about why that makes sense. It has to do with this property that I haven't really mentioned explicitly yet, which is the following. So it comes from an intuition. So let's start with the intuition. I keep saying value looks, any one of these values, looks like it has this type for up to k steps. Or some expression looks like it behaves like tau for up to k steps. What does that sentence suggest? For anything less than k, it better also look like that, right? Does that sort of answer your question? That's why it's okay to say for all j, as long as it's strictly less than k in this definition. Yeah? Okay, another way of answering that question is, you have a fold V, but you might not use it right now. So you might not do your unfold right now, and then you need to know that the underlying value is good for 99 steps. You might hang on to this value, and other parts of your program might run and use up your step budget, just like I was saying before with lambdas, right? And at some later point, you might, when you have, let's say, 5 steps left, you might actually unfold that fold. So
I guess the concern would be like, I have this bucket with the v underscore piece of k, right?
Yeah.
And I take a value out of it.
Mhm.
And I say, well, because it's coming from piece of k, I know that I can, let's say, unfold it 100 times.
Yep.
But then I start unfolding it, and oops, it didn't work because it was actually coming from v sub 3, for example. Right? So
It has to be safe for all the smaller ones.
it has to be safe for all the smaller ones, for all j less than k. Yeah, yeah. So it's stronger than what you're imagining, right? It's not that it exists. Yeah, yeah? Okay, all right, good. Okay. All right. Let's see. So where were we? We've proved part B, I think. And now let's talk about how we would prove part A, because you agree, right? Like if we've just sort of sketched out the proof for part B, if we can now prove that any syntactically well formed expression, any E that's well typed, belongs to our logical relation at those types, then we have our proof of type safety done, right? Okay, so basically just like yesterday, now we have to prove lemma A, right? And we have to prove lemma A by induction on this typing derivation for E, right? So we're going to have one case for every single typing rule in the language. And for every single rule, we'll have to prove that, assuming that it's syntactically well typed, you have that it's semantically well typed. So let's do one case of the proof. Let's do the unfold rule, right? So there's the unfold typing rule right there. I'm going to push the definitions up, so please stare at the unfold rule. It's about to disappear. Okay. All right. So we want to prove lemma A. And the case we are considering, is for the typing rule for unfold. Actually, I'll write it. Unfold E has type tau with new alpha tau for alpha if E has type new alpha tau. Right? Okay, now, we have this. We need to show that unfold E is semantically well typed, right? So here's what we need to show. Okay? Actually, before we go on, this downward closure property, let me just write down a lemma that spells out something that I just said a couple of minutes ago. So we have this property, I said, that if something looks like it has type tau for k steps, then it should look like it has that same type for fewer steps. So if you have some v that belongs to v of tau for k steps, and you have some j that is less than or equal to k, then it better be the case that v belongs to the v relation at type tau for those fewer steps. Okay? This is called, sometimes we call it downward closure. More formally, we call it monotonicity. Okay? The intuition is simple. I've said it already, right? If you look like you have type tau for up to k, then you clearly should look like you have that type for fewer. So this monotonicity lemma is helpful because it comes up when you're proving various cases of lemma A. By the way, lemma A is called the fundamental property. Let me say that. The fundamental property This is a term you'll see in the literature a lot. Anytime you read a paper with a logical relation in it, they'll show you the entire logical relation, and then the first theorem, the first serious theorem, not lemmas, that they prove will be the fundamental property of the logical relation. It's also called the basic lemma of the logical relation. Essentially, what it is something of this shape, which says, if you're syntactically good, then you belong to the logical relation. Okay? Yeah, we'll talk about it, what it is for binary relations later. All right, so coming back to this. So this lemma is, there are a couple of interesting things to say about this before we move on. So how would you prove a lemma like this? What would you do induction on? I wanted to prove it. How do I start? I have to prove it for all tau, right? Any type tau. So we're going to prove it by induction on the type structure. Or you could more formally write it by induction on the derivation of tau being a well-formed type. But let's just say by induction on tau. Okay, so you're going to have a case for every single type. So let's see. For Booleans, vk bool. If I have a value that belongs to vk to the Boolean value relation for k steps, can I show that it belongs to it for fewer steps? Yes, because the definition doesn't even use the step index, right? Okay, so the Boolean case is easy. All right. Tau 1 or tau 2. This one's actually really interesting. And I'm not going to do the proof, but I want to tell you why. And I would like you to do this as an exercise later on today. One question you might ask with, I don't know, maybe you might ask it. Sometimes this comes up, that for the value relation for functions, why is it that we say for all j less than k? Like, if you naively try to define this, you might say, how about we try to write it as something like tau 1 or tau prime, lambda x tau looks like it has that type. If for all arguments that belong to the argument type tau, how about we just put a k there for k steps? Then, after we do the beta reduction, that thing looks like it has the result type tau prime, also for k steps. How's that? Is that bad? Would you have naively come up with that if I hadn't drawn timelines for you and all that? I think it's a perfectly legitimate thing to start with. If you were trying to do this, you probably would start with that. Okay? But this is a problem. The technical reason, the super technical reason, is that if you work with this definition, you will not be able to prove this monotonicity property. Okay? You will not be able to prove that a lambda that looks like it has this type for k steps also looks like it has that type for some fewer steps. Okay? More intuitively, the problem has to do with the fact that, we have, it has to do with the contravariance of the argument. Okay? But I'm going to leave it at that. And I think it's a very interesting exercise to actually try to push this proof through, first with the bad definition and see how you fail, and then with the good definition and see it succeed. Okay? All right. So, with that to the side, let's go back to the proof of unfold. So, we want to show that this unfoldy expression is in our logical relation, right? So, let's start looking at definitions. We're going to prove this statement. So, we're going to say, suppose that we have a k greater than 0, and suppose that we have some gamma that is good for k steps, all right? And then what we are required to show next is going to be gamma wrapped around our unfold expression belongs to the E relation for k steps at the type tau. I'm just reading off of there, mu alpha tau for alpha. With me? Yes? Okay, good. Now, yesterday I said let's push in substitutions. Let's push this substitution in. So this is equivalent to showing unfold of gamma E belongs to that. Same thing. Okay, so that's what we have to show. So we have to show that unfold of something belongs to the E relation. All right. Let's go use our induction hypothesis. What do we know by our induction hypothesis? Well, we have this smaller derivation up here for E, right? So by induction hypothesis, we have that E is semantically well-typed. Right? Okay. Now, we have this statement. This statement says for all k, for all substitutions. So let's instantiate that statement. Instantiate this with, let's pick a k. Well, we have this k over here that we've already supposed is greater, and we have a substitution, so let's instantiate this with k and with gamma, right? We better, and whatever gamma we pick, we better be able to show that it's in that interpretation for k steps, which we already have, right? Okay, so we know that this is in that interpretation as required, and therefore what we get now, therefore we know that little gamma wrapped around this expression E is going to belong to the E relation at the recursive type. E relation, recursive type mu alpha tau for k steps. Right? Good? All right. Okay. Still have to show this thing. Unfold of this gamma E. But now we know that this gamma E belongs to that E relation. Okay. So what do you think we should do now? Let's look at what we have to show. This is what we have to show. Unfold of gamma E belongs to the E relation, right? Okay. So in order to show that unfold of gamma E belongs to the E relation says, well, consider some arbitrary j that's less than k, right? Are we going with less than, or do we want to make it less than or equal? Oh, no, sorry, that one is less than. Okay, so suppose that j is less than k, and suppose that your unfold gamma E expression steps in j steps to some final, I'll write EF, okay? Such that EF is irreducible. And now what we're required to show is that this EF belongs to the value interpretation of our expanded type for the remaining number of steps. K minus J. Good? Okay. All right. So what should we do now? Is this hard to follow in the afternoon after lunch? Kind of. We're morning lectures for proof. Okay. So this is what we want to show. What do we have? We know that our unfold gamma E takes steps and reduces down to some value, and we're interested in showing that that value belongs to the value interpretation. But we know that the underlying term gamma E belongs to this E relation, right? So let's look at what this is telling us. This is telling us that by the operational semantics, it must have been the case that somewhere along the line, the first thing that you did was take your unfold of gamma E, right? And in some number of steps, let's just call it J prime for now, you got gamma E down to a value, right? Or something irreducible. So this must have reduced to some sort of E prime, right? Such that this is irreducible. That must have happened, right? And what do we know about this? Well, so either this could be our final stuck term, maybe this is EF, right? Which would be the bad scenario. So we know that J prime is something that's less than or equal to J. So this I just did by just inspection of the operational semantics. That must have happened. If you are saying that unfold E reduces down to something irreducible, then along the way this thing must have gotten down to something irreducible. But now we have a fact, right? We know that gamma E reduces to E prime, which is irreducible. We can take this fact that we have, instantiate it, right? Okay, so now I'm going to instantiate this. Let me just put a star. This fact here, star, with E prime, and I know that E prime is irreducible, and I know that this reduces, I know that gamma E reduces to E prime in some J prime steps, and the J prime is less than or equal to J. Well, if J prime is less than or equal to J, and J is strictly less than K, then J prime is strictly less than K, right? I need that. That's what the E relation is saying. All right? So, note J prime is strictly less than K, so we can actually instantiate star, which is about K steps, right? And therefore, what do we get? We get that this E prime belongs to the value relation at this type. For K minus J prime steps. Okay? All right. What were we required to show? We were required to show that unfold E gets down to some final thing, and that final expression EF is in the value relation of the big type. But if we know that this, right, so basically now what we know, we want to show that unfold of this E prime. By the way, this E prime has to be equal to some V. I'm going to start calling it V prime. We know that it has to be some V because it's in the value relation. So I'm going to call it V prime. Okay? we have to show that this unfold V prime belongs to, we have to think about what that can do. So if you have an unfold V prime, actually it's better than that. If E prime belongs to this value relation, what shape does E prime have to have? Look at the definition for recursive types. Has to be a fold, right? So this thing must be equal to some sort of fold V prime. So what we've just done is we've said we can go from unfold of gamma E to unfold of E prime, and we've said E prime is actually a fold of V prime. So unfold of gamma E has, in some number of steps, which I'll put down later, well, J prime steps, has reduced to unfold of fold of V prime. Right? Unfold of a fold can take one more step and get us to V prime. Right? So that V prime must be our EF. I've taken this reduction, I've got it down to a value, I can't go any further. That thing must be this irreducible thing, EF. Right? Now we therefore know that V prime is equal to the EF prime, to the EF that we wanted to show is in this value relation. Right? Okay. Now what we know from here is that fold of V prime is in the interpretation of the recursive type, right? For K minus J prime. Right? Okay, so if you look at the definition of recursive type, it tells you that the underlying value for any fewer steps belongs to the expanded type, which is what we want to show, right? So now we still want to show, just to repeat, that our V prime belongs to V of tau, mu alpha, tau for alpha, right? And we still need to show that it's for K minus J steps. Let's add up our step budget. How many steps did we take? We took J prime plus 1. J prime plus 1 is equal to J, right? Okay, so I'm going to instantiate this fact that we have, this one right here, with K minus J prime, which I know is strictly less than K minus J. And then that lets us complete our proof. Okay? Yeah. Say that again? Here, initially, all we knew is that the J prime must be less than or equal to J, right? But when we got here, we knew that the E prime is actually a fold of V. And then when we stuck the fold of V under the unfold, we realized that we have to take another step. And then we sort of looked at that, and that budget has to add up to J, and therefore that means that J is equal to J prime plus 1. Okay? So we are taking a step and getting smaller, and that is why we can instantiate our definition, this definition, with the smaller number, K minus J, and get what we need. Yes?
So you said, you know that V prime has to equal EF while assuming A that's true. Do we have to prove that? Like, how do we actually know that?
So I've been kind of playing fast and loose with this definition of irreducible. Irreducible says that you have an expression to which you simply cannot apply another reduction rule, right? So irreducible, any expression, should formally be defined as there does not exist an E prime such that you can take a step. Does that help answer the question? So you have to be able to show that, but you're doing that by saying a value by definition cannot take any other steps. As in, we can look at the operational semantics and there are no steps that, a value can't be stepped to anything further, right? EF, by assumption in the proof, right here, is irreducible, which means that it cannot take another step. So, and the semantics is deterministic, so they have to be.
So we need to know somehow that if E is reducible to V1,
Mm-hmm.
and V1 is irreducible, and E is reducible to V2, and
Yeah.
V2 is irreducible,
Yeah.
and V1 is equal to V2. Like, I'm thinking if we were to formalize this proof, would we have used that as a one?
Yes. And that would fall out from the fact that your operational semantics is deterministic. Yep. Mm-hmm. Okay. All right. Any other questions? So basically, I've done one case of the proof for you because I wanted to do. Oh, sorry. Yes. Yeah? Sorry, say that again?
So there are three cases in the downward closure.
Yes. Mm-hmm. Yes. Recursive types are easy.
Okay.
Maybe not trivial, but not interesting either.
Okay.
Yeah. And by the way, this downward closure lemma is something you end up needing when you do the case for lambda, for functions, for the lambda typing rule. I believe you also need it in application, yes. Okay. All right, so that's the basic idea of step index logical relations. Now what I'd like to do is I'd like to talk about not just type safety, but rather how do we do logical relations for equivalence, okay? So I'm going to change what we're after over here. Let's talk about contextual equivalence. Now, you guys talked about observable equivalence or observational equivalence or contextual equivalence last week. And logical equivalence. And you actually showed that Dan showed, I assume, that for simply type lambda calculus, logical equivalence and contextual equivalence coincide, right? Sorry? Oh, you did it for system F. Okay, good, even better. Okay, I'm going to just do it for the language that we have up on the board, this language with recursive types. Okay, so let's define contextual equivalence. Did Dan talk about the fact that contextual equivalence is hard to prove directly because of the quantification over all possible contexts? Yes? Okay, good. Yes? Okay. All right. So contextual equivalence. So I want to define when two expressions, E1 and E2, actually are contextually equivalent. Let me change things up a little bit. I'm not going to define equivalence. I'll define approximation, and then I'll define equivalence in terms of it. You'll see what I mean in just a second. So I'm going to use a less than sign. Okay? E1 contextually approximates E2 at the type tau. Now when I write that, what I have in mind is that E1 has type tau under gamma and E2 has type tau under gamma. I'm not going to put that up on the board, but that's my assumption. They're both well typed. I have typing derivations for them. They have type tau under gamma. All right. So contextual equivalence says that for all possible contexts C that have a whole of the correct type, okay? And I don't know how Dan was writing this, but I'm going to write it for all C such that C is well typed with a whole that can express, that can take expressions that have type tau under the environment gamma. In other words, expressions like exactly these two guys, E1 and E2. And when you plug a hole with an expression that type checks like this, you get back an expression that will be closed and have some type, you put bool here for starters. Okay, so for all contexts of that shape, is this okay? Have you seen this sort of notation?
I think you might have called it observation.
Okay, but they're the same thing. Yeah. Yes, yeah, other than that. But did he write types for contexts like this? Good. Okay. All right. So if I have a context with a well-typed hole, and when I close it, I get back a closed term. This is saying that the C of E1 and E2 will be closed. And if I know that C with E1 well, this is a non-terminating language, so I can just say if C of E1 converges, then it must be the case that C of E2 converges. Now that's not what Dan did last week, right? He must have said the context has a result type bool. If this thing evaluates to V, then that thing evaluates to V. Or maybe as an if and only if, because I'm doing approximation and he was doing equivalence, right? Okay. In a language where all programs terminate, you see, contextual equivalence is about making observations, right? So when you say I'm going to pick any arbitrary context and you say, I'm assuming that the final result of the program is a Boolean, if you have a terminating language, you better be able to say that this evaluates to some V, which will be true or false, right? Then this evaluates to the same V, true. Either they're both true or they're both false. This is a non-terminating language. And you don't no longer have to actually inspect the value that comes out of the program. From the point of view of observational equivalence or approximation, the only observation, the one that sort of trumps all the others, is does it converge or not? Because if I write this definition saying that if this terminates, then this does, right? Or you can read it as if it's an equivalence, it would be an if and only if, right? That is sufficient, because if your context terminates, if you actually know that you can tell two things apart by, because you can produce a context that gives you true in one situation and false in another, then you can always put an if then else around that context and build a slightly bigger context that terminates on true and diverges on false. See what I'm saying? Yeah. Okay, so this is a classic thing. You will see that in the literature, anytime contextual equivalence is defined for terminating languages, you have to look at the value you get out, but anytime it's defined for non-terminating languages, you only have to see whether they both converge or both diverge. Yeah?
And you're intentionally defining this to have an implication in one direction.
I'm intentionally doing it, yes. And if I did make this an equivalence, then I would do this. And that's it. Okay? But why did I do it this way? Just to kind of show you another way of doing things, which is rather prevalent in the literature. You can define contextual approximation, and now you can define your usual notion of contextual equivalence, which is that, by simply saying that in both directions. So this is defined as E1 approximates E2, and E2 approximates E1. Okay? Conjunction. This makes your life slightly easier in certain settings. You can then also, you can just do all your proofs for approximation, and this immediately falls out. Okay? Like you can define, so what I'm going to do now is actually, let's edit our logical relation to make it a binary logical relation. So now you know that doing proofs of contextual equivalence is hard to do directly because of this quantification over all possible contexts, and that's why we use methods like logical relations, right? Okay, so up here we have a logical relation. This is unary because we defined it for type safety. Let's make it a binary logical relation. We want to construct one that is sound with respect to our definition of contextual equivalence for this language. What does soundness mean? Did you talk about that? It means that if you can use, I want to set up a logical relation. Let me start here. I'm going to make my relation binary. In fact, I'll put a normal turnstile here. I'll say E1 logically approximates E2 at the type tau. Okay, I haven't edited anything else yet, but at the top level, this is what I want. I want to construct a binary logical relation. And what I'm after is, if I can use this logical relation afterwards to prove that a program E1 and E2 are logically related like this, right, then it better be the case that E1 contextually approximates E2 at the type tau. Okay? And you can, again, change both of these to equivalences. It would be the same idea as what we were doing on the other board. Okay, this property is soundness. If you can use your proof method to show two things are related, then they are, in fact, they are contextually approximate. So this direction is soundness. Completeness goes in the other direction. I'm just going to edit in place. Completeness says that any two things that are contextually equivalent, you can use your logical relation to prove that they are contextually equivalent. Okay? Stronger property. But if all you're interested in, so in certain applications of logical relations, you will definitely want a logical relation that is both sound and complete. Okay? I'll talk about that in a couple of days, just a little bit. But if all you want to do is you want to define a logical relation so that you can use it, sort of turn the crank as a proof method for proving programs equivalent, then you just need to know that it's sound. Okay? If you're actually, the thing you're after is doing contextual equivalence proofs, then you use the logical relation instead, and you need to know that it's sound with respect to contextual equivalence so that you know that you're using a legitimate proof method. Okay? All right. So let's sort of look at how we would go about making this binary. Let's start right here. So now I want pairs of expressions, or pairs of values. All right? So I want to define a value relation v tau. It'll still be indexed by types, but it's going to be binary, right? So it's going to say a v1 and a v2 look equivalent, or rather they have this notion of contextual approximation, right? Under some conditions. Okay? So I'm going to keep using the word related. So this is easy for Booleans. true is related to true, false is related to false. Right? We really don't want true to be related to false or vice versa. Right? Okay, so that's easy. That captures our notion of equivalence for our base case. How about functions? Well, now by the way, I'm going to put up notes for this part so you don't have to write down. I know I'm editing in place and I know that's annoying when you're writing notes. So just watch. Okay, now we want to say that two lambdas, lambda x e1, lambda x e2, are related at the type tau arrow tau prime for k steps. If you give me two related inputs, I will give you back two related outputs. As opposed to one input with the property of interest, I will give you some output with the property of interest, right? Okay, so if you give me, for all v1 and v2, that belong, oh, I edited the wrong line. Too close. Okay. For all v1, v2 that are related at the argument type tau, right? If this was Boolean, then these would both have to be true or both have to be false, right? Okay. Then we are going to produce two programs, E1 with V1 for x and E2 with V2 for x. And these are going to be related in the E relation for the remaining number of steps j at the result type tau prime. Right? Very easy. Edit. I'm going to just go through and make everything binary. Fold is easy too. We have a fold v1 and a fold v2 related at the recursive type if the v1 and the v2 are related at that type. Okay. Now let's do the only interesting case. I have two expressions, E1 and E2. I want to know if they're related at the type tau for k steps. Okay? So, maybe it's a moment to say something. These logical relations that I've been showing you are operational in nature, right? When I say what it means for certain terms to be in the relation, in my definition, I appeal to running the terms, right? The E relation shows you better than any other place. If I want to know that E behaves like something of type tau, I say, run it. Let's see what happens, right? If I want to know now that E1 and E2 are equivalent, in this case, approximation, right? So what I want is if E1 behaves in a certain way and gets to a certain value, then E2 will also converge and get to a value, and both of those values will be related. Okay? But this operational notion, I'm like sort of, that's why the operational semantic is defined first, because we use it in how we express whether things are in the relation or not. This is very different from the denotational or categorical logical relations that you guys have been seeing, right? These are very operational in flavor. That's how we give semantics to types, so to speak. Okay, so what do we do here? Well, E1 is related to E2 if, by the way, this time I'm going to assume that I'm building my entire relation out of well-typed terms. Okay? So I want you to assume that whenever I have a V in the V tau relation, that V is actually well-typed. Like that. Okay? And similarly, whenever I have an expression E that I'm putting in the E relation, I want to make sure that that expression is closed and well-typed. This should be pairs of values and pairs of expressions. Okay? Remember yesterday I said I'm not building my relation out of well-typed terms. I don't have derivations for them. Today I'm not doing that. I'm saying let's build our relation out of well-typed terms. Because now we're not interested in proving type safety anymore. Okay? Assume that your type safety proof is done. It's off to the side. It's over. And now you are defining a logical relation for equivalence. In this you can talk about things being well-typed. Okay, so now what do we want to say? E1 related to E2 at the type tau. I'm going to say for all V1, such that E1 in j less than k steps reduces to a V1. Now notice I can say value. I don't have to talk about irreducible. If it's well-typed, it's not going to get stuck. Right? Okay, so if V1 reduces to V1 in j steps, then there has to exist a V2 such that E2 reduces to V2, and the V1 and V2 are related in the value relation at type tau for the remaining number of steps, which is k minus j, just as before. Anyone want to complain about what I just wrote? Infinitely more gas, yeah. Right. So I'm saying that I have a budget, right? I told you that before. We have a budget. I only have k steps. But this time I have, well, think of it as you have k steps to tell them apart, is usually how I like to say it in English, only it's a slightly misleading notion. I'll come back to that in a second. Okay, so what am I saying? I'm saying if E1 reduces to a value in no more than your budget, in some j less than k, right? Then E2 will converge, but I'm not saying in how many steps. Could be more than k, could be less than k. In other words, my budget is not affecting the other side, so to speak, the second expression. All right? Okay, and then I say that the V1 and V2 will be related in the value relation at the right type for the remaining number of steps k minus j. Okay, now, why does my budget not affect the other side? That should be the question, right? Intuitively, the answer sort of is that this whole budget explanation works really well for intuition, but if you look at what this means for equivalence, you really don't want that k to cap the budget for evaluation on the other side. Because if you did, then the logical relation that falls out of such a definition will do the following. It'll say E1 and E2, really, they can only always reduce to values. They're only considered equivalent if they reduce to values in the same number of steps. It may not look like it. I can make that a J1 and I can make that a J2. But in the end, when you sort of unfold all the definitions, start with the base case 0 and build up, you will have a definition that is getting at a notion of equivalence that you don't actually want. The notion that we want is contextual equivalence, and contextual equivalence is very liberal with respect to how many steps each side can take. It only says that both sides have to converge or both sides have to diverge, right? And that is why we don't want to limit this with k. Or at least that's my intuitive explanation of why. Okay? All right. And then we basically repeat the same exercise. Here, instead of substitutions to a single value, we'll have substitutions to two values. And we'll make sure that the V1 and the V2 belong to the V relation of that. And here, right, I modified the top level first. So we're just going to do the same thing for all k greater than 0. If you have a substitution, which is now giving you pairs of values for your x's, I'm going to use, I'll write it like this. Gamma 1 means if x maps to V1, V2, then get all the x mapped to V1s. That's what gamma 1 is. Use that to close off the term E1. Use the other one, gamma 2, which again would be x maps to all the V2s. Use that substitution to close off your other expression, E2, right, for these two sides. And then these two closed expressions need to belong to the E relation at the type tau. Okay? So we've just fully edited this logical relation to now be a binary logical relation that you will be able to prove is sound with respect to contextual approximation on the board. Yeah?
So if we have no restriction on the number of steps we would take,
Mm-hmm. Yeah?
then does it make sense to define Vk minus j for
So basically what I want you to think about is here, in all of these cases, right, this is the place where it becomes obvious that the budget is only about the first term. It's not about the term on the right-hand side. The budget only applies to the term on the left. In these definitions, that part is not becoming obvious, but it's still there. So we're writing it like this, but there's only one spot in the definition which makes you sort of aware of this asymmetry with respect to the budget. But the asymmetry, therefore, then carries through the entire logical relation. Yeah? Is there a question? No. Yes. Sort of?
You're saying that we're actually asserting something stronger than we need, or are you saying that this Vk minus j will suffice for the induction?
The k minus j will suffice for the induction. to work out. And the word induction is really the key thing here, right? These step indices, I mean, in the type safety proof, I was motivating them with budgets and all of that. But in the end, the step index logical relation trick is a trick to make sure that you get a well-founded logical relation, right? It does not demand that both sides adhere to some sort of step budget. It's a trick to get an inductively well-defined definition. Okay? And then when you use tricks like that, you have to think about, well, what is the sensible outcome? Like, what would I do in this case of the definition? And actually, you know, this goes back to about 2006. Alex is here. Alex was my office mate at Harvard when this was sort of being worked out. The first time when I was trying to define one of these step index logical relations and prove that it was sound and complete with respect to contextual equivalence, I was trying to do a binary version. The unary versions existed at that point. That was my earlier sort of dissertation work. I tried putting J1s and J2s that were both less than K and doing all sorts of other funny tricks. But with every model that you constructed, what actually fell out when you played with examples is that I'm constructing a relation in which both programs had to take the same number of steps. And this was really bizarre. But, you know, that was, so since then we've sort of learned that this is the right way to do things. Yes? Yeah.
Which means that if I have an expression that actually takes more than that much time to reduce,
Yes.
it's trivially linear relation.
Yes.
But this relation is actually symmetric. And
It's symmetric. Yes. So let's make it symmetric, right? Instead of doing all this approximation business, suppose that I was trying to actually define the relation that was not doing approximation but was doing equivalence. Let's do it because it's actually quite nice. You'll see that exactly what you're saying is about to fall out. If this was a logical relation not for approximation but for equivalence, how would we edit this part? And really, this part is the only part you would edit, right? Because this part is the only part where you're saying, I'm going to run E1 and then E2 better do the same thing. So now we also want to say, I'm going to run E2 and E1 better do the same thing. So we're going to augment it. I'm going to say and, so this is one conjunct. I'm going to say and for all V2 such that E2 reduces to V2, there better exist, oh, this is an implication. There better exist a V1 such that E1 reduces in any number of steps, and now you have to put the values on the right side still. V1, V2 are related. So we just make it an and. And if you don't edit it like that, then the original one, you can, at the very top level, you can say E1 is equivalent to E2 if E1 approximates E2 and E2 approximates E1. That makes sense. Yeah? Oh, I'm laughing because many people have observed over the years that shouldn't we be able to use these step budgets to somehow, define equivalences where we can talk about, hey, this program is actually more efficient or runs in fewer steps than the other one. It doesn't quite work out so easily. Just going to say it doesn't quite work out so easily. Yeah. You see, because, okay, it does not capture that in a technical sense, because here I'm limiting this with J, but I'm saying this can be anything. So it could be fewer or more.
Oh, I see.
Yeah, right? I'm not mandating that this side be.
Some examples.
Yeah.
You need this symmetric relation.
Yeah. Okay, all right. I think it's time to stop, right? So what you should do is, it's definitely time to stop. So I would recommend that you definitely try the cases of the monotonicity lemma that I talked about for functions. And for this logical relation, try proving the fundamental property. Oh, by the way, what is the fundamental property now? No, I have to write down one more statement. The fundamental property of this logical relation, the theorem that you are after, is that if if you have an expression E that is well typed, then it is related to itself. Notice they're not two E's, just one. Okay? The fundamental property, especially when we get to binary logical relations, this becomes utterly obvious. It's sort of like a reflexivity condition. It's saying that you have defined this relation properly so that the term is at least related to itself. Now that means a lot actually though, right? Because it's saying you can give me different but related inputs and I will run the same program on those different inputs and get possibly different but related outputs. Okay? And this is also essentially like, I start writing this as equivalence, it's a parametricity kind of thing, right? That's how you state parametricity limits. All right. So you might want to prove a few cases of the fundamental property. Lambda and application are interesting. All right. Stop there.